Okay.
I am delighted to welcome back virtually to Athens, our former student, Rene Erlin Castillo, who graduated from Ohio University with a PhD under the supervision of Archil Gulisashvili a few years ago. Let's leave it at that. And he is now at Universidad Nacional de Colombia in Bogota. And once again, thanks to the marvels of modern communication, we have established contact, and we hope to have Rene in person in Athens for a visit maybe in the near future. But in the meantime, we get to talk mathematics with him. So it is my pleasure to present his talk about the Laplace transform. So Rene, please feel free to share your screen or do whatever you need to do.
I'll be on my way, yeah. Everyone is seeing the screen?
Yes, we do.
Okay. So I'm ready to, we're ready to start?
Yes, go ahead.
Okay. Okay, first of all, I'd like to thank Sergio Lopez for his kind invitation to participate in this colloquium today. And when I have the opportunity to be in a remote reunion via Zoom, Google Meet, etc., the jet sums came to my mind. The reason for that is because in the 60s, the jet sums transported us to the 21st century in a beautiful fantasy that in which today is reality. All of you remember the jet sums?
Yes, we do.
All right. Okay, that's how things goes. Okay, anyway, let me go into business. This talk is aimed to general audience. However, it has two levels, namely undergraduate level and graduate level. All of us have a background on Laplace transform, doesn't it? Our first touch with the Laplace transform has a lack of region. What I meant by that is when we apply the Laplace transform methods to solve, for instance, a non-homogeneous linear differential equations with a constant coefficient, we did it without having a very careful about the hypotheses when they are valid. In other words, why is justified to take the Laplace transform of both sides of the equation? A similar situation came up when we need to take the limiting side of an integral. This always fraught with danger, especially an improper integral. In this talk, I shall present the results which allow us to apply rigorously the Laplace transform. Let's start, remembering or getting a recording that Laplace transform is an example of an integral transform, as is defined in here, okay? What is the pencil? I cannot. Okay, as we see here, it is the Laplace transform, and What happened? Okay. Yes, okay, then let me go. And the first thing that we have to take care is we suppose that the f is a function real or complex on the real line, and s is a real complex parameter. The Laplace transform is defined as this limit. I meant that it is an improper integral, properly speaking. So now we need a couple of definitions to deal with the Laplace transform. Both of them are, the first definition state that f has a jump discontinuity at one point if those limits exist, but they are different. And the other important definition is a function is said to be piecewise continuous on the invert if the limit when t goes to 0 by the right exists and is continuous on every final invert except possible at the final number of points at which f has a jump discontinuity. One of the important property of a Laplace transform is its linearity. Okay, we take two functions and it's just that the Laplace transform of each is finite, then we can see that in fact the Laplace transform is linear. The second result most of the time goes unnoticed. This is say that if we take a function in L1, the Laplace transform send the function to the bounded space of functions. I will go back to this result later on in the talk, which is something, it belongs to the part of the graduate level. Okay, here came the Weierstrass approximation theorem. Is something pretty good about this theorem. When I was checking in the history about these theorems, I realized that Weierstrass came up with this result at the age of 80. It means that we have some chance to do something else. Okay, that's good. And the Weierstrass approximation theorem will help us to prove the second lemma. And the second lemma will be the cornerstone for to prove that in fact the Laplace transform is a one-to-one operator, which is the following theorem. But previously we need a definition which is state that the function is exponential, has exponential order alpha if there exists a constant positive one, shows that this inequality up here happen, okay? And the theory state, we said that we have two continuous functions with exponential order. Then if the image of the function through the Laplace transform are equal, then the functions are equal, which means the function is one-to-one. Okay. Now, here there is a theorem. There are some misprint here. They have to be something like the limit as s go to 0. Okay. We got this result, which state the continuity of the Laplace transform, right? Okay, once we know that the Laplace transform is a continuous operator, we can move on. And I need to pass the another screen. Okay. The other theorems is where the other theorems say that if we got a piecewise function which is continue on a piecewise continuous function on the half line, and the Laplace transform is another function with respect to the parameter s, and the improper integral is convergent, then this limits, we got this limited, which means that the limit pass inside of the integral, something that I refer at the beginning of the talk. But anyway, the following results state that f is a piecewise continuous on the half line and of exponential order, then the Laplace transform exists for the part of the real lines, I mean, the real part of the complex number, and converge absolutely. That's another important result that will allow us to apply the Laplace transform. As a corollary, we got the following result, which state that indeed the Laplace transform converge uniformly. And theorem 7, which is the only one that has a level here, is quite important, and it's something that we expect since the improper integral is related with some series, and in detail, the series goes to 0 when the argument, or when n goes to infinity. It is kind of result. This result is kind of the thing that I am talking about. Now let's check some examples. Two of them state that the first one, that we can obtain the Laplace transform for functions which indeed do not satisfy, they are not of exponential order. And okay, let's see how this thing works. We might notice here that the function is, the Laplace transform of the function exists, and also we got that the function, the second one after the integration by part, we see that the function is as order alpha with alpha equal to 0. However, the sign of e raised to t squared, okay, is as I said, is of exponential order 0. Okay, let's see the other example. Now we got another function which is no piecewise continuous. We might see there is no continuous at 0, but is bounded when for t greater than or equal 1. But we shall compute its Laplace transform, and in fact, it is the function square root of pi over s. Is another example of a function which is now piecewise continuous on the half real line, and the Laplace transform exists. Okay, it is one of the situation, the regular one that we have in undergraduate classes. We like to take the series, the Laplace transform of some series. This one is finite, but we like to take this in term by term. We'll see what happened here. Okay, the Laplace transform of a polynomial of degree n have this expression that we see on the screen, and this comes with the help of 4. And now, let's see what happened with the infinity series. We got the function which have a Taylor representation series as we see there. And if we take the Laplace transform, we will get this series, which is divergent accordingly with the ratio test that we can see there. Now, how do we can apply the Laplace transform to an infinite series without problems? Here are the conditions that have to satisfy the coefficient of the infinite series. As we might see in here, this expression for those that are acquainted with complex variable, it is reminiscent of Cauchy estimate, right? And this makes some sense because if we see this function in the sense of a complex function, it is exactly analytic function, right? And we can apply Cauchy estimate or Cauchy theorems, all those kinds of things. And that makes sense with our theorem back here, right? Now let's check some example. We get these functions, a well-known function sine t over c, which has this series representation. And as we might see in this conclusion, the coefficients satisfies the condition of the theorem. And now we can apply the theorems and get right here the Laplace transform as we wish. Okay, let me see what happened. Good. Okay, here comes one important lemma, which states that if the derivative of a function is continuous and also of exponential order, then the function is of exponential order. Okay, this is important at the moment to apply the Laplace transform to differential equations like this one here. Okay, they will allow us to take term by term the Laplace transform, and as the theorem state, the solution of that linear differential equation of order nth, the solution is continuous and of exponential order. That is important. We have to check this hypothesis before to apply the Laplace transform to linear equation like this one in here. And those two results are quite well known in any book of Laplace transform. And okay, now here came the inverse of Laplace transform, which is at the level of undergraduate courses. It just stay without proof. It is because to prove these theorems, we will need the Laplace convergence theorem. But by the way, for Riemann integral functions, the Laplace convergence theorem is valid too, okay? So it means that at the level of introduction to analysis, of this kind of level, we might prove this result because we have available such a theorems, right? And here is the inverse Laplace transform. And its proof is very interesting. As I said, it is a base. We need to use the Laplace convergence theorems as a tool to prove these important theorems. Okay, now we have to move, we are moving to the graduate level. Here we got an interesting definition, which is about the distribution function. By the way, I learned here, I learned this notation from Archer. He was the guy that taught me about this notation, and I like to. I haven't used a lot. Okay, this function has a very, very interesting properties, and we can just gather a few of them. I know I didn't put it in here, but it's a decreasing function, and we are just measuring the level set of the function f. But okay, now we got the well-known Minkowski integral inequality, which will be helpful for proving some I mean, it is so important in operation theory to use these results to show the boundedness of many different operators in many different spaces or spaces related with LP spaces. Also, we got here this interesting result. We got a name, is a Cavalieri principle or defensive name. Is also called layer cake representation. That will be also of the great help for the common result. This theorem down here this one, this result, okay, I cannot write.
Uh-oh.
Okay, this result is a kind of a Parseval identity, and that will be of useful for the coming result. Okay, but before to go to the main result of this talk today, we need to refresh this well-known result, which is that the duality, the not duality of LP, right? And here we go. If we got a function in a Hilbert space, L2, then the Laplace transform is bounded in this space. And here, we know this is just the square root of pi. Okay, good. Let's just check a little quick the proof of this result, and we will get the help of the Minkowski integral inequality to prove this result, as we might see down here. After some chain of variable, we transform the Laplace transform in this expression, and after that, we go over the next step, and here goes the application of the Minkowski integral inequality. All right, okay, now we move to another step. We got a function in LP with P living between 1 and 2, and also we got the strong boundaries of the Laplace transform. For this proof, we need the Calderon-Sigmund technique, which states that we can decompose a function by truncating the function on its range, and we just get two functions, one which is named a good function, and the other one which is named the bad functions. Also, we prove, we can see there, that the bad function is weak bounded in L2, and the good function is, I cannot see here where it is. Okay, is down here. Let me see. This proof that the good function is weak bounded in L1, and the bad function is weak bounded in L2. For a moment, we might think that we got a kind of interpolation theorem, but in the end, we will not need to interpolate it. We just use the Cavalier principle, and with this thing will be enough to get our result. Okay. All right. Here we go. Okay. Now, since the Laplace transform is linear, we got this since I'm here, and also by the properties of distribution function, we got this inequality in here. Then we move down and apply the Cavalieri principle, which is in here. Let's see, okay, here. I cannot write this. Okay, here is the Cavalieri principle, and with the assistance, with the help of this inequality, we move down in the proof and get this this result down here, which is the thing that we was looking for, that the Laplace transform is strong bounded in LP with P greater than 1, less than 2, and we might see the reason down here in the constant. I mean, in here, let me see. Okay, that's the reason that P has to be living in this interval. Okay, so now let's see the next result. Now we got, if we take a function in LP with P greater than 2, less than infinity, we also get the strong bounding of the Laplace transform. And in here, we will use the duality result. If we take a function in LP with the conjugate numbers, P and Q conjugate, and since P is greater than 2, then we get that Q lives between 1 and 2. And hence, by the above theorems, we have this bounded. And also we apply them here, the duality result. And here came the partial identity, right? As we might see here, they just commute this one with this guy here. And up in here, we apply the Helder inequality and the condition that the norm in the dual is 1. So we get this bounded, okay? And in this way, we have proved that the Laplace transform is bounded on LP for P living between 2 and infinity. Okay. Now let me erase the scenes and move to another result. Okay, as a corollary, we got that the Laplace transform is bounded for P between for P greater than or equal 1, less than or equal infinity. This part here, the part when P is equal infinity was the first remark that I pointed out at the beginning of the talk. So as a remark, we might see that indeed the Laplace transform take functions in LP and send to LP, okay? Which is a good result, right? Okay, now we are about to finish, but let's stay the definition of Laplace-Stillger transform in LP. We will need in this part of the talk this measure, all right? That will be of particular interest in order to deal with the Laplace-Stillger transform. Okay. Okay, the Laplace-Stillger transform is defined in this way. Okay. We also can define this in a little bit different way, but that it is the one that I choose for the talk today. Okay, let's see something about this transform. Okay, we got as a first result that for a function in LP, the Laplace Stilger transform exists. And also we got in the second theorem that for the Laplace measure, the boundedness of this result of this transform is take this form. We might see here, it is the measure defined at the beginning, and this one is the Laplace measure. Okay, this kind of combination, we have to take a function on the space where the LP with the Laplace measure, and this function will be on, I mean, the transform will be on the LP space with the new measure, okay? So let's see. All right, in here we got the adjoint of this operator. I mean, in the formally we got that the adjoint of the Laplace transform of a Laplace Stilger transform has this form. I mean, this one. Yes. I cannot write. What happened? Okay, well, we may see this is the conjugated or adjoint operator of the Laplace transform. The Laplace Stilger transform. So okay, that is the last result. State that the adjoint of the Laplace Stilger transform is bounded, and as we expect, there is the boundedness, the norm is in the other way around at the first one, right? Look that in here, we got the new measure, and here the Laplace measure, and in the other result, we got the new measure here and the Laplace measure in the other norm. Okay, so it is all that I have to say today about the Laplace transform. Part of the last part is right now on the review, and these other results will be appear in Cuestiones Mathematicae, but this paper is I mean, we study the Laplace transform on the rearrangement in invariant spaces, and for this particular paper we use the K method for proving the boundedness of Laplace transform, but we just was able to prove just for LP with LP, I mean in this interval. So we are now investigating if we can just extend this thing out of this interval. All right, it's all that I have to say. As I said, thank you for having me, even remotely. Any question?
Thank you very much, Rene, for a very nice talk. Does anybody in our audience have any questions or comments for our speaker?
Where is Archie? I don't see him.
I'm here. Yes, thank you,
Oh.
Rene. It was interesting. I don't have any special comments.
So
I would like to participate with a comment.
go ahead, Camilo.
I don't know if you can share again your presentation. When you talk about distribution, you say that there is this property that you have the integral, an improper integral of a function times the Laplace transform of other function, and then you can like switch the Laplace transform to the first function and the second function without Laplace transform, and the integrals are the same, the improper integrals.
Mm-hmm.
So that's a very nice property, and I have seen some very difficult and tricky integrals which are calculated via that property. So that's a very important property.
Yeah, this is called a parser one.
Yes, that parser
type of formula or identity. That is useful. Let me tell you something. When we want to prove the LP boundary of the Hilbert transform, okay? And I don't know if all of you are acquainted with the Hilbert transform, but I would like to take the opportunity, and this coming July is coming a book of mine, which name is Fourier meets Hilbert and Ries. And in that book, it is aimed for a course like Fourier analysis classes, this kind of stuff. Okay, it will publish by the Gruyter, but it's something that I don't like. I was discussing with the editor, but this is too expensive book. Okay, so I hope that Martin get one for the department.
So the more you sell, the more money you make, Rene?
You know, I need to pay the Irene school. I mean, she's now going to university. Now, as all of you knows, you know, we do not make too much money when we write a book. Okay, it's just for the own satisfaction. And when we got a group, the seminar, the student can write theses, master thesis, PhD thesis, that would be, I mean, enough pay for the author. Okay.
Okay, anybody else, any questions or comments for our speaker?
Sorina, hello. Here is Sorina. I didn't recognize you. How are you? I cannot hear you. Your microphone is off.
Hello, nice to see you.
Oh, hello. How are you?
It's okay, quite okay. Tired, but and with these problems in Europe, but it's okay.
Sorina is in Switzerland.
Sweden.
Sweden. Sorry, anytime I confuse.
Oh,
Yeah,
it's okay.
yeah.
It's 11 p.m. there.
Yeah, it is Karstadt.
Yes.
Is
Yes, yes.
yeah.
Good to see you.
Good to see you too.
We have a tradition in this seminar that it is hard to applaud now because there's too much noise with the distant communication, but we shake our hands to applaud. But if everybody turns on their cameras, then I can also get a group picture. So everybody who can, please turn on your cameras and I'll take a group picture. There are some cameras that are still off. Maybe people are shy. Maybe the camera won't turn on.
Here I see Edison Rojas, but he doesn't turn on the camera. Benigno Parra.
Benigno is there, and I would love to see him, but sometimes his Wi-Fi is a bit challenged, he has told me.
Yeah, it's worse because he's in Venezuela. Here is Edison.
Edison is here, so I'm going to count till 3. Everybody smile. 1, 2, 3. We have a group picture, and it will be posted in the Department of Mathematics Facebook page. So there you go. You're famous now. Thank you, Rene, once again.
Thank you.
Thank you.
Thank you for taking the time, and thank you everybody for taking the time to join us this evening. And
it was very nice to see you, Archie.
Same here.